अभी चेक कर लो, इस वॉइस इज क्लियर है कि नहीं, बोलो। इज am I audible to all of you? Tell me. Audio. Right. And you can use the code of Reddy to avail the great discount offers. Right. Now you can see now here West Bengal Electricity Department का so नया बैच भी हमने लॉन्च किया. You can have a look at. Officers call, crash course is running. So Nakshatra batch, and so the other thing is Unacademy Una. There are three modes are there. You can see now voice mode, quiz mode, smart summaries. And with this you can directly talk to Una, so we can clear all your doubts. And there is a smart summary, so you can upload the document, you can ask to summarize all the content. So these things are very helpful well before going to the exam. And so April 1, so onward the test series which is live, you can have a look at now. The number of tests topic wise 29, so single subject 10, advanced subject, multi subject, full length mock test, 12-year PYQs, and total how many are there? 77 test series. And Unacademy offer the two types of subscriptions. One is plus wala, the other one is iconic. सो हियर प्लस में आपको क्या चीज मिलेगा? टॉप एडुकेटर्स क्लासेस मिलेगा, लाइव डाउट्स, एवेल्युएटेड मेंस टेस्ट सीरीज, इसके साथ स्ट्रक्चर्ड कोर्सेस एंड पीडीएफ, लाइव टेस्ट, अनलिमिटेड एक्सेस. आइकॉनिक में क्या मिलेगा? पर्सनल कोच मिलेगा एंड फिजिकल नोट्स भी आपको मिलेगा. राइट. And according to your time slot, you can book your Unacademy mentorship program. These are the GATE 2025 rankers from Unacademy team. या चलिए हम शुरू करेगा. या इन प्रीवियस क्लास ये और सारा टॉपिक हमने कंप्लीट किया. एंड लेट्स कंटिन्यू आवर डिस्कशंस. ओके, टेक दिस वन. The magnetic forces. So here forces acting on a charged particle. Now let us consider a charged particle Q is present inside the electric field. Then you tell me now, if we have a one charged particle present in the electric field region, so what type of force the charged particle will experience? You tell me now. And what force the charged particle can experience? And we have the electric field this direction. And the charged particle will experience a force this. And what type of force the particle will experience? You tell me now. So this is the force because of the electric field. That electric field force we are calling it as Fe. What is this electrostatic force? You tell me now. The electrostatic force which is given as Q into E. And if it is a positive charge, the direction of force is same as electric field directions. Now this is a force acting on a charged particle. Now from this we can able to get the acceleration. As we know, acceleration is given as net force by total mass now. So that means Fe by m, then it is given as what I can say, tell me now, Qa by m. This is the acceleration of the particle. Okay. This is the acceleration of the particle. If you observe here, this acceleration of a particle which is proportional to 1 by m. Acceleration of a particle which is proportional to what, tell me now? 1 by m. If the acceleration is high, so for what particle now with the mass is low? Now if we compare this electron and a proton, whose mass is high, you tell me now? Electron and proton. So if we see this thing here, acceleration of electron by acceleration of proton, which is equal to what I can say, this is mass of proton by mass of electron. So you can see now here mass of proton is more. Mass of proton is more compared to mass of electron. So that's why what I can say now, acceleration of electron is more compared to acceleration of proton. Okay. This is the force acting on a charged particle in the presence of electric field. Now let us talk about in the presence of magnetic field. So if we consider I have one charged particle Q, the charged particle which is moving with a velocity v, and assume that we have a magnetic field in the region of this particle, magnetic field which is in the cross inside. Now the charged particle will experience a force, and what force will experience? You see this thing here. If I consider the particle is the present in the presence of both electric as well as a magnetic field also. Electric field is there, magnetic field is also there. Then the charged particle will experience a forces because of electric field as well as magnetic field. So that means what is that force, you tell me now here? That is a force due to the electric field plus what I can say now, force due to the magnetic field. And the electric force हमने देखा ना, we have seen the electric force acting on a charged particle which is equal to Q into E. And the magnetic force acting on the particle is what, tell me? Q into, that is V bar cross B bar. Q into V bar cross B bar. Then F, which I can say this as what, tell me now? Q into, we can say this as E plus V bar cross B bar. This is the total force acting on a charged particle in the presence of both electric and the magnetic fields. Total force acting on a charged particle in the presence of both electric and magnetic field. Yeah, this force which is called as a Lorentz force. This is called as a Lorentz force equation. Right? This is called as a Lorentz force equation. Fine, all of you? Now, so that means the particle will have two forces, electric force as well as magnetic force. Now, let's talk about this electric force. We have discussed now, we'll talk about the magnetic force now here. Tell me about this magnetic force now here. This magnetic force Fm, which is equal to what I can say, this is Q into what we can say, this is V bar cross B bar, and this Fm, which is equal to what we can say now here, that is BQV sin theta, isn't it? BQV sin theta, where theta is what, tell me now? Angle. Theta is an angle between velocity and the force. Now you tell me now, if theta equal to 0, what happens? Theta equal to 0, theta is an angle between velocity and the magnetic field, then the magnetic force is 0. And if theta equal to 90 degrees, theta is 90 degrees, then we have the force is maximum. And how much that force is? So here QVB, and that force is a maximum force, right? Now, done. Now you see this thing here. If you talk about the nature of this electric and magnetic fields, you see this thing here. And if you talk, you see the direction of this magnetic force. However, the direction of this magnetic force, you tell me now. The direction of this magnetic force, which is perpendicular to velocity. And so this is perpendicular to velocity, and this is also perpendicular to what we can say now, tell me now, displacement. It is also perpendicular to displacement, isn't it? Perpendicular to displacement also. Velocity we can write as rate of change of displacement, right? So we can write as perpendicular displacement also. Now from this, if we talk about this work done, what is this work? You tell me now here. Work is equal to force into displacement, F dot dl. So this work, which will be equal to, see the what the angle between the force and displacement is 90. If the angle between the two vectors is 90, dot product will becomes what? Tell me now, 0 now. So how much is work done in moving a charge in the magnetic field is 0. Yes, isn't it? Yeah, you see this thing here. In case of electric field, you need to observe some important observations here. I have taken one charged particle. For the charged particle, we apply the electric field we applied. We applied the electric field we applied. Yeah, you tell me, when we apply the electric field to charged particle, under the effect of this electric field, what happened to charged particle? What is the nature of electric field? You tell me now. As we know, nature of electric field is what nature? Diverging nature. We know the equations of the Maxwell's equation are del dot E, which is equal to what? Tell me. That is rho V by epsilon, and del cross H, and which is equal to what? Tell me now here. J we have seen now. From this, what is the nature of electric field? Is a diverging field, and nature of magnetic field is a rotational field. So when we apply the electric field to charged particle under the effect of electric field, the charged particle will do the diverging nature. The particle will move like this. Okay, will diverge. So, and whereas the same charged particle, when we applied a magnetic field we applied, tell me what happens. Under the effect of this magnetic field, what is the nature of a magnetic field? You tell me now. Rotational nature. Under the effect of this magnetic field, so the charged particle will do this as a rotational motion continuously. It will keep on, will rotate in this circular path, isn't it? So this means it will keep on, will rotate. So from this, what I can say now here? From this, so what, as a result, if a particle is in a circular motion, displacement is 0. Displacement is 0, so that's why this work done is what? Tell me now, 0 here. But in this case, work done is non-zero. We have a displacement is there now. Okay. Electric field is what nature? Diverging nature. Magnetic field is a rotational nature. Okay. Understood. So this is a conclusion we can give from this now. When the electric field is applied, so what you tell me now, applied to a charged particle. So under the effect of electric field, the charged particle will possess what property? Diverging property. Charged particle will possess diverging property. As a result, what happens now? The velocity of particle may increase or may decrease. Velocity of particle may increase or may decrease. That's the reason electric force is called as what force is a accelerating force. Electric force is called as a accelerating force. Okay. So when the electric field is applied, the velocity of the particle and kinetic energy of the particle will changes. Okay. But whereas the same thing if I do for this thing in a magnetic field, under the effect of magnetic field, the charged particle will possess what property? Rotational property. Charged particle will possess rotational property. So the work done is zero now. Why? Because the displacement is zero. So always इसमें ऐसा घूमेगा ना. Displacement is zero. That's why there is no work done. The magnetic field cannot change the magnitude of velocity, but it can change the direction of velocity. Magnetic field cannot change the magnitude, but it can change the direction of velocity. It can change. So that's the reason we used to call the magnetic force is also called as a deflecting force. Magnetic force is called as what force is a deflecting force, but electric force is called as accelerating force. It will accelerate. And electromagnetic field what can do? If the particle moving this direction, because of this magnetic field path changes. That's why the magnetic force is called as the deflecting force. Okay. Next. And so let's find the direction of this magnetic force. How we can find the direction of this magnetic force now here? To find the direction of this magnetic force, we use right hand thumb rule we can use. And the Fleming's left hand rule is there, and the other way we can use other way we can use a right hand rule. That is what you can see now here. As we know, F is equal to Q into what tell me now here? V bar cross B bar. Now, so let us consider I have one charged particle Q and this particle moving with a velocity V, and assume that this we have a magnetic field is like this cross. What you need to do here? First you place the four fingers along the velocity. So first velocity direction we have placed now here, and you try to place on a paper on your notebook. On your notebook you place it, and thereafter what we should do here, and the magnetic field is where now into the board now, so I need to move fingers downward direction. When I move fingers downward direction, so the direction of thumb is where you tell me now? Thumb is upward direction, you see, like this. And so this is the direction of the magnetic force. Okay. Now, if we have a charged particle, and let us assume that velocity of a particle is like this, velocity of particle like this, and the magnetic field is like this, cross. Cross means what? Tell me. Into. Now velocity is upward direction, magnetic field is where now? Inside now. Magnetic field is inside, so thumb is left side. So this is the direction of the magnetic force here. Okay. So by using the right hand thumb rule, we can get the direction of this magnetic force, so can be calculated. Okay. Next. Yeah, you can see one problem. A magnetic field of B exists at a point if a test charge moving with a velocity given experience no force at a point. The electric field at that point is. Now the charge is experiencing no force. Basically, the particle moving under the effect of both electric field as well as a magnetic field. So that means the total force acting on the particle is what will be now? Electric force plus magnetic force, right? The sum of electric force plus magnetic force. And so that is the net force, they are saying zero na? No force the particle is experiencing. So that means what I can say, tell me now here, E plus, that is V bar cross B bar, which is equal to 0. No force means. So from this, E is equal to what I can say, minus of V cross B. So that is E means I can interchange now B cross V. Okay. Now, so let us find out now here, this is E, which is equal to, and this is I cap, J cap, K. So B, how much is B value? Tell me now. 1 coefficient. So this is 2 and this is minus 4. And this is, we have 3 V naught minus V naught 2 V naught. So you can tell me now, this is E equal to, this is I cap into, yeah, closing this row and column. So it will come to be a 4 V naught plus 4 V naught. No, minus na, plus again minus. Minus J cap into what, tell me now here, 2 V naught plus 12 V naught. Yes, next plus K cap into what, tell me now here. So this is minus V naught minus 6 V naught. So how much is E value, tell me now here. So this term 0 minus 14. 14 V naught into J cap minus 7 V naught into K cap. This is what I'll be now, minus V naught. Minus V naught common, so which is equal to 14 J cap plus 7 K cap. So what's the option you see? That is option B. Okay. Next one. Now let us talk about the path of the charged particle in a uniform magnetic field. Let's see the path. So here the force acting on a charged particle, which is given as what, tell me now, QVB sin theta. QVB sin theta. QVB sin theta. So if theta equal to, so here, so based upon the theta, the force will depends upon the theta, isn't it? Force will depends upon theta and the path depends upon force. So from this we can conclude that the path of a particle will depends upon the angle between the velocity and the magnetic field. Yeah, if the theta equal to 0, what happens? theta equal to 0 or 180, then what happens? And theta equal to 0 or 180 means what? Tell me now here. We have the magnetic field and we have a magnetic field and we have a charge. The charge is moving like this. And how much is angle? You tell me now. In this case, angle theta equal to 0. Or some other case, if this is the magnetic force, magnetic field, the charge is moving this direction. This is the velocity. Here in this case, theta value, how much you tell me now? 180 degrees. Now you tell me now, what is the force between them? Which is equal to 0. What is the force between them here? The force between them which is equal to 0 now. If theta equal to 0, that means the charged particle does not experience any force. If the particle does not experience any force, what happens now here? The particle does not experience any effect of magnetic field. इसका मतलब the particle have no effect on the particle does not feel the magnetic field is present now. So the particle will move whatever the path initially the particle is moving, the same path the particle will continue. So from this we can say this as what? Tell me now here. The particle will move in an undeviated straight line path. The path is what we can say? Straight line path. Okay. Done. Next, let us say here theta equal to 90 degrees. Theta is 90 degrees means what? Tell me now here. Now let us consider we have this magnetic field is like this. Now let us consider we have my charged particle. Here is a charged particle and this particle velocity is upward directions. Velocity upward direction and magnetic field is inside. Okay. Now you tell me now. Then see what happens. You tell me now here. So the direction, so the angle between them is 90 degrees now. So can you tell me the path in this case? What happened? How the path is? So here, and you see the direction of force. You tell me now first of all. Velocity is upward directions and field is inside. So this right side na left side direction of force, isn't it? As a result, the path of this particle, it will come to be like a circular path. The direction of this magnetic force is toward the center. When the particle reaches here, this is the velocity direction. So here, this is the velocity direction. And here, this is the velocity direction. Right. Now, at this location, the direction of magnetic force is this direction now. And here is the direction of magnetic force. Magnetic force direction is like this. At all these locations, the direction of magnetic force is where you tell me toward the center. So now this is the magnetic force acting on a particle. So how much this force now here? Magnetic force, that is Q V B sine theta. Theta value 90 degrees. As we know, if any particle in circular motion, it has a centripetal force is there, and the required centripetal force is provided by this magnetic force, that is mv square by r. R is a radius. So required centripetal force is provided by this magnetic force, that is Fm equal to what I can say now, Fc. So that means QVB, which is equal to what, tell me, mv square by r. So we will get cancelled. So from this, R is equal to what I can say, R is equal to QB by, sorry, R equal to MV by QB na? MV by QB. Right. So this is the radius. R equal to mv by qb. Now we'll convert this. V is the linear velocity. We're converting to angular velocity. That is what, tell me now, V is equal to r omega. V equal to r omega. So that means R equal to, that is m into r omega by what, tell me now, QB. R will get cancelled, so that is omega equal to what, tell me now here, QB by m, where omega is the angular velocity and the time period we can calculate, that is equal to 2 pi by omega. So that's why the time period will come it as what, tell me now, 2 pi m by QB. 2 pi m by QB. This is the time period. Right? And from this we can get the frequency also. So frequency means what, tell me now, 1 by t na. So that is F is equal to QB by 2 pi m. According to requirement, we can able to calculate these parameters. Right? Next. Now let's see this thing. If theta is other than 0, 90, 180, then what will happen? Theta is not equal to 0, not equal to 90, not equal to 180. Then what happens? In this case, what will happen? So let us say we have this magnetic field is like this, and I have one charged particle Q. The velocity of a particle is like this. Velocity of particle is like this, and there is some angle between the velocity and magnetic field. Now this angle is theta, where this angle is not 90, not 180, it is not 0. So let's see what will happen. Then I can resolve this velocity into two components. This is one component, this is the other component. This velocity, which we can say this as a V parallel, and this we can say this as V perpendicular, where this V parallel, which is equal to what, tell me now, V cos theta, and this V perpendicular, and which is equal to what, tell me now, that is V sin theta. Okay, now you see this thing here. Now velocity has a two components under the effect of, so this V parallel and B, and both are same direction. If both are same direction, the path is a straight line path. And because of V perpendicular and B angle between them is 90 degrees, because of this the path is a circular. So that means what here, V parallel makes a straight line path, V perpendicular makes a circular path. As a result, the combination of these two, you see this thing, this will move in a straight line, and so this is a circular path. As a result of this, the path of a particle, it will come to be like this. The particle will move in a helical shape. As a result, the path of the particle will becomes what, you tell me, helical. Right. Now, what is this radius, you tell me now here? Here, which velocity makes the particle to circular motion? V perpendicular. That is given as R equal to M into V perpendicular by QB. And that equal to what we can say? MV sine theta by Q into B. This is R. And whatever time period you tell me, that is 2 pi m by QB. 2 pi m by QB. Next. Now the distance, so from here to here, this distance which we used to call as a pitch. This is called as a pitch of the helix. Pitch. Pitch of helix is how much? And pitch which is equal to which velocity makes the particle to move horizontally? That is V parallel. So we can say V parallel into what, tell me now here, with the time period is T. So the pitch of the helix is V parallel equal to V cos theta. V cos theta into T. Time period is what, tell me now, 2 pi m by Q into B. Okay. Got it? Done? Now let us find the force acting on a current carrying conductor. So earlier we have seen force acting on a charged particle. Here the force acting on a charged particle is what, tell me now? That is Q into V bar cross B bar. This is the magnetic force. Magnetic force on charged particle. And force acting on a current carrying conductor, which is given as F is equal to I into, this is L bar cross B bar. This is the magnetic force on conductor. Right, this is the magnetic force acting on a current carrying conductor. Right? And so from this, that is which is given as scalar form, which we can write it as what I know, BIL sin theta. Scalar form BIL sin theta. So as usual, if theta equal to 0, force is 0 now. if theta equal to 0 degrees or 180 degrees. In this case, so what is this magnetic force on a conductor? 0. If theta equal to 90 degrees, then this magnetic force is BIL, maximum force. Right. Now how we'll get the direction of this magnetic force? Same as we have seen earlier, right hand thumb rule. Like earlier we have seen F is equal to Q into, that is V bar cross B bar, right? So earlier we place along V direction, we will place the fingers now. Now what the formula in this case now? In this case, F is equal to I into what, tell me now? L bar cross B bar. So we need to place the fingers along the current directions here. Here we need to place the fingers along the current directions. Okay, first you place the right hand fingers along the current directions and move the right hand fingers along the direction of magnetic field. Then the right hand thumb gives the direction of magnetic force. Okay. Now if we have considered this, here is a conductor. Let us say this conductor carrying a current is upward directions. On this conductor, assume that there is some magnetic field is there, that is a cross. Magnetic field is there, cross. Can you tell me the direction of this magnetic force on this conductor? First we need to place the fingers along the current directions like this, and we have to move towards the magnetic field. So this is the direction of force now. Now this is the direction of the magnetic force on this conductor, isn't it? Now if I place my conductor like this, now you tell me now here, if I call this the direction of magnetic field is this direction and the current is like this. Now you tell me now here, so this is this direction of magnetic force, this is the direction of magnetic force. Okay, like that we can get the direction of this magnetic force, we can calculate. Right? And force between two parallel current carrying straight conductors. And consider we have two conductors, two parallel conductors, and these are carrying length almost very long length conductor. These two are carrying the current in the same directions, and this current is I1, this current is I2, and this length is L1 and this length is L2, and the distance between these two, which is equal to D. Okay. Now because of the first conductor will create some magnetic field on second conductor, and the direction of this magnetic field on the second conductor, which is along what direction, cross now. Because of that, because of this magnetic field caused by first conductor, the second conductor will experience certain amount of force, and that force we need to find now here. This is the force acting on second conductor because due to first conductor. So what is the F21 is F21, which is the force on conductor 2 due to conductor 1. Okay, so you tell me now that force, how much that force and the direction of force we need to see. That force F21, which is equal to what I can say now, that is B I L sine theta. So here the magnetic field caused to first conductor, on the second conductor the length is this thing, and the angle between the magnetic field and the current is how much? Current is upwards, field is inside, so the angle is 90 degrees now. So theta value 90. So that means what happens to F21, which is given as B1, and this is I2 L2 into sine 90. Sine 90 value 1. So that is F21, which is equal to B1. Magnetic field because of infinite length conductor now, that is given as mu naught I1 by 2 pi r. R means distance is d na. I1 I2 into L2. So that means F21, which is equal to mu naught. This is I1 I2 by 2 pi d into L2. Now from this, which we can say this as F2 1 by L2, which is equal to what you tell me now here, this is mu naught I1 I2 by 2 pi d. This is a magnetic force now, magnetic force per unit length. Okay. Now similarly we can able to find because of the second conductor. So you see this thing, second conductor will cause a certain amount of magnetic field on first conductor. So this is what direction now? Dot outside now. So this is, we can say, B2. Now I am calling this as force acting on the first conductor due to second conductor. This is what I can say, tell me now. Magnetic force this is the force on conductor 1 due to conductor 2. So you can tell me now what is this F12, which is given as B I L sine theta. So this B means what we can say here? B means what we can say here? Magnetic field because second conductor due to first one, and this is length is, whose length is now L1. Theta is 90 degrees now, so B12 will becomes as what, tell me now? So that is B2, that is I1 L1 into sine 90 degrees. So that is F12. B is equal to what, tell me now? Mu naught I2 by 2 pi d. This is I1 L1. That is F12 equal to mu naught I1 I2 by 2 pi d into L1. Okay. Now you can see this is F12 by L1 which will come to be a what? Tell me now. Mu naught I1 I2 by 2 pi d. This is the magnetic force per unit length on the first conductor because of second one. You see this thing, both the forces are equal, you see. Both the forces are equal, isn't it? F12 by L1, F21 by L2, both values are equal. Okay. And we'll get the directions now here, tell me now. And whatever the direction of this magnetic force you see, now how we'll get now here on this one, current is upward direction, field is outside. Tell me now, upward direction, field is outside. So this is the direction of the magnetic force now. This is F12. And here the current is upward, field is downwards. So here current is upwards, field is inside, like this now. So this is the direction of F21. So you see this thing, both the forces are in the, so this is type of force is called as what force, you tell me now? Attractive force or repulsive force? And this force is called as attractive force, right? So from this we can conclude this as what, tell me now? The force between the two conductors when they are carrying the current in the same direction is what type of force? Is an attractive force. If the currents are in the same direction, if the currents in the two wires are in the same direction, then that force is what, tell me now here? Attractive force. And if it is opposite direction, and that is a repulsive force. And finally the magnitude of force is given as what we can say, tell me now? That is F by L, which is equal to what, tell me now? Mu naught I1 I2 by 2 pi d. This is the magnitude of force. Done. Next one. Electromagnetic fields. Electromagnetic fields. Right. In case of electromagnetic fields, the conditions is what, tell me? So how the charges, you tell me now? Charges are moving. How they are moving, you tell me now? The charges are moving with some accelerations. Charges are moving. Yes, I told you now, this electromagnetic field stuck, we will complete it. Charges are moving with an acceleration. Right. So in this case, we have what electric fields, and which is depends upon x, y, and z and time, and magnetic fields which also depends upon x, y, z and time. In this case, electric field will depends upon magnetic fields, and the magnetic field will depends upon electric fields. So in this case, we can say electric and magnetic fields are interdependent. Electric and magnetic fields are interdependent. So in this case, what we can say, these are called it as, what, tell me now here, these are time varying fields. Time varying fields, or which we can also call them as, what, tell me now, dynamic fields. Okay. And these fields are called it as, what, tell me now, electromagnetic fields. These are called as what? Electromagnetic fields. Okay. Fine. Now, so first let's talk about the Faraday's law. And what is the Faraday's law is the Faraday's experiment. So here what he did, he has taken one conductor. As we know, whenever there is a flow of current through a conductor, we have a magnetic field. We have a magnetic field around the conductor like this now. Whenever there is a flow of current, we have a magnetic lines like this. So Faraday has tried the reverse. Is a vice versa is possible or not? He has tried. So because of the current, we are getting a magnetic field. Let us see, due to the magnetic field, do we have a current or not? Okay. Then he got this idea. He tried his experiment. He created some magnetic field created like this. He created the magnetic field. In the magnetic field region, he placed one conducting loop. He placed one conducting loop, and one end of this conducting loop he placed one ammeter. One end of conductor he connected to some ammeter. So he has created some magnetic field, and that magnetic field, which is a function of x comma y comma z comma t, which is a function of x comma y comma z comma t. So when he did his experiment, he observed that there is no deflections in the ammeter. No deflections means what? And the current is zero. That means there is no flow of current. So here, in this case, he observed that there is no flow of current. In this case, he created some magnetic field which depends upon only on the space, depends upon x, y, z only. Right. And next case, what he did, he created some magnetic field, and this magnetic field is a time varying magnetic field he has created. He created the time varying magnetic field he has created like this. and one end he is connected, he also connected to some. One end he has connected to one ammeter. Now in this case, he observed some deflections in the ammeter. In the second case, he has taken the magnetic field which depends upon the space as well as time also. Which depends upon space and time also. When he observed that one, he found that there is some deflections in the ammeter. Deflections means what, tell me now? So look, there is some current is there now, some non-zero current is there, isn't it? So from that he has concluded his experiment. What here the conclusion he made? Or the conclusions he made? Static magnetic field does not produce any current. And time varying magnetic field will induce an EMF in the closed circuit, induced in closed circuit, which causes the flow of current. Okay. So if the magnetic field is a static field, it does not produce any current. If it is a time varying magnetic field, will induce an EMF in the closed circuit which causes the flow of current. Right. From that he has given the statement. Yeah, these are the conclusions. Static magnetic field does not produce any current. Time varying magnetic field induces an EMF in the closed circuit which drives the current. And from that he has given the statement of the Faraday's law. The induced EMF in any closed circuit is equal to time rate of change of its magnetic flux linkage. Okay. So the induced EMF, and which is in a closed circuit, that's why closed line integral of E bar dot dl which is equal to what, tell me? The time rate of change of its magnetic flux linkage. And this lambda is called as a magnetic flux linkage. Since it is opposite direction, that's why we have a negative sign. And that negative sign is a contribution of a lens. We'll discuss about the Lenz law little later. Let's focus about the Faraday's law. Where this lambda is called as what, tell me? Magnetic flux linkage. And this lambda which is given as n into phi. Lambda is given as n into phi. Right. Fine. Now, so this EMF, which is given as closed line integral of E bar dot dl, and which is equal to minus of, so this is a number of terms n into, we can say, d phi by dt, where phi is the magnetic flux. Flux is given as surface integral of B bar dot ds, magnetic flux. If we place now here, we will get it as EMF, which is equal to closed line integral of E bar dot dl, and which is equal to minus n into, that is d by dt of flux, which is equal to surface integral of B bar dot ds. Okay. If we talk about the number of turns, which is equal to 1, if we consider this EMF, which we can write it as what, tell me, this line integral of E bar dot dl, which is equal to, now, so this is surface integral of minus of, we can say this as dou B by dou T dot ds. And here this left side we have a closed line integral. We can apply the Stokes theorem. From Stokes theorem, what we can say, tell me now. So this is open surface integration of what, tell me now, del cross E dot ds, which is equal to what, tell me now. So this is surface integral of minus dou B by dou T dot ds. Okay. From this, what I can say, tell me now, del cross E, which is equal to minus dou B by dou T, I can write now. And this is the modified form of the second Maxwell's equation. Earlier we have seen the Maxwell's equation, that is del cross E is equal to what we have seen, 0. This is applicable only for static fields only. Only for static fields. Right. So this is the general equation. This is called as a second Maxwell's equation. This equation applicable for all the cases. This equation is valid for all type of cases. This is applicable. Okay. So from this we can write, you see this thing here, del cross E, which is equal to what, tell me now, minus dou B by dou T. From this, what we can say, this curl of electric field is non-zero now. If the curl of the electric field is non-zero, what I can say, electric field nature, you tell me now. Electric field is called as what, tell me, A, rotational or irrotational. If it is zero, irrotational, non-zero now. So from this, what I can say, electric field is a, electric field is what type of field, you tell me now? Rotational field. Electric field is a rotational field. Static electric field is what type of field? Static electric field is what type of field? Static electric field is irrotational. A rotational field. Okay, but electric field means dynamic electric field. Yeah, rotational, non-conservative. Yes. Okay. Done. Next. Now here you see this in different type of analysis we are going to see now here. So as we have seen this EMF, the induced EMF equation, what we got, you see this thing here, EMF, which is equal to, yeah, so which will be equal to what, tell me now here, this is minus of d phi by dt, and this EMF, and which is equal to what, tell me now, minus of d by dt of, yes, now phi is equal to what, tell me now, flux now, yes, which we can say this as what, tell me now, B bar dot A bar na flux. So that means if only B changes, B changing but area is constant, then what is the EMF, tell me, which is equal to, we can apply this thing, this derivative only for B only. So here dou B by, this is dB by dt dot of A bar, okay, in this case. So in this case, what we have, tell me now here, only magnetic field is changing, area of the loop is constant. So what we'll call this type of EMF, this type of EMF, which we used to call as a transformer EMF. Time varying magnetic field, but loop is stationary, and this is also called as a statically induced EMF. Statically induced EMF. Okay. Next one. If the magnetic field is constant but area changes, only the area is changing. In this case, what we can do here? So this EMF, it should be equal to what, tell me now, minus of d by dt of what, tell me now here. So we can say now B dot A, BA cos theta, we can say now. So here, which is constant, which is variable. So in this case, area is variable. So we can apply for the derivative only for area only. So that is dA by dt into what we can say, tell me now, cos theta. Okay. And so if we have considered the scenario like this, now let us say this is my x-axis and this is my y-axis. Consider we have the conductors are placed like this. These are the conductors which the conductors are placed like this. Now this conductor is one is freely movable conductor. Here we have magnetic field which depends upon only space only. And this conductor can oscillate freely back and forth. And so this length, which I can say fixed L, and this is X if I call. And here theta, which is equal to 0. So then EMF, which is given as what, tell me, which is equal to minus of B. So here into d by dt of what I can say, this area is given as L into X. So here we can say theta value 0. So we'll get this EMF as what, tell me, that is minus BL into what I can say, dx by dt. Then will come to be a what, tell me now here, that is minus BL, rate x is the displacement na? Rate of change of displacement is nothing but what, tell me now, velocity. This is scalar form. And the vector form, how we can write the equation, you tell me now, EMF, and which is equal to, this is equal to V bar cross B bar dot L bar. And this EMF, which is called it as a, this EMF, where we can find this type of EMF now? Where you can find this one? So this is what is changing here? The conductor is moving now here, this area changing. So this is called as a, you can find this type of application in all the motors now. That's the reason this is called it as a motional EMF. This is called it as what, tell me now? Motional EMF. Yes. And this is also called as a dynamically induced EMF. Dynamically induced EMF. Okay. Motional EMF or dynamically induced EMF. Next. And the third case, if B and area third case, case 3, here what we are taking, B and area constant, but the angle is changes, rotation is happening. So this means B flux is equal to what we can say now here, BA into cos theta. So we can write the EMF as what, tell me now here in this case. Yeah, if we have number of terms are there, we can say N dA cos theta, which is equal to minus of d phi by dt na. So this EMF, which is equal to minus of d by dt of phi is equal to NBA cos theta. NBA cos theta. So that is EMF, which is equal to minus NBA cos, differentiation is sin theta into d theta by dt. What is the d theta by dt is a rate of change of angular displacement, is called as angular velocity, NBA omega into sin theta. So this is the EMF in this case. This EMF is called as what, tell me? Motional EMF, rotational EMF also we can say. This we can say this as a rotational EMF. Here what changes? Angle changes. So that's why this is called as a rotational EMF. And which we can also call this as a flux cutting EMF. flux cutting EMF, or we can also call this as a dynamically induced EMF. Okay. Yes. So finally we'll conclude all the EMFs. You can have a look at. See this thing here. EMF. La 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 la. Ha, 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 ha. All the EMF we can conclude it as like this. If the magnetic field is changing with the time, that is a statically induced EMF. If the area changes, we can say this as a dynamically induced EMF. So in the dynamical induced EMF, again we have two cases. We have the conductor cuts the flux lines, and if the theta changes, or we can say the motional EMF, we can also call them as a rotational EMF. La 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 la. Right? Done. Next one. Lenz law. Lenz law. The Lenz law, which is used to find the direction of induced current. To find the direction of induced current, this Lenz law, which is applicable only for the closed loops only. Why? Because the Lenz law is the current. When there is a flow of current, you tell me now, if it is a closed path, then only flow. So that's why it is applicable only for the closed conducting loops only. And this is based upon law of conservation of energy. And this is the consequence of Newton's third law, action reaction. What is this Lenz law? You can see now. It states the current flows in a closed conducting loop in such a direction that it tries to oppose the cause producing it. The direction of induced current is such a manner it opposes the cause producing it. So here, जिसने उसके फायदा किया करंट ऐसा बहता है कि उसकी नष्ट करना चाहता है जिसने उसे फायदा किया उसे पैदा किया उनको नष्ट करने का डायरेक्शन में ये फ्लो करेगा. Is this point clear to all of you? Right. So the direction of induced current is in such a manner it opposes the cause producing it. Fine. Now here take this problem. So by applying the Lenz law, we should find the direction of the current. Look at now here. Find the direction of induced current. Here they mention that magnetic field is increases. Here you tell me now, if the magnetic field B, actually the magnetic field is cross means inside. B value increasing. If the B value increases, so that means how the induced field, you tell me now. Induced field should be what direction now? Should be oppose. Opposite means what direction, you tell me now here? Dot now. If it is dot, so that means the direction of current is like this now. So the induced current direction is what direction I can say? This is a anti-clockwise direction. Understood this point? Tell me. Next, here in this case, B decreases, magnetic field decreases, so that means how the induced field now here should support or oppose? Should support. Support means what I know, same direction. So the direction of induced magnetic field is same direction, means cross only now. So that's why the induced current is what direction? So this means cross. It is decreasing now. So this way is clockwise. All of you tell me. Next, here the magnetic field is what happens now? Increases. If the magnetic field increases, how the induced field now should support or oppose, you tell me now. It will oppose. It is opposes means what direction now here? It is opposite to original field. So that means how the induced current now, tell me now. So this is the clockwise. Okay. Now in this case, magnetic field decreases. So if the B decreases, how the induced field, you tell me now. Induced field is what direction? Should support or oppose? It should support now. Support means what direction, you tell me now here. This is same direction, means dot only. So that means how the induced current, you tell me now. This is anti-clockwise. Okay. Next, boundary conditions. Boundary conditions. So any medium will have their three parameters will have. The mediums are classified based upon the three parameters. Those are called it as what, tell me now? Mu, epsilon, sigma. Mu, epsilon, sigma. Right. Mu, epsilon, sigma. These are. And these are called it as what, tell me now? These are called as. No, yeah, this is the last topic now. Why to waste the time? So then it will complete. Before 5 o'clock we'll finish, don't worry. Before 5 o'clock we'll finish. Okay. Why break again? Mu, epsilon, sigma. And these are called it as what, tell me now here? Medium parameters. These are called as what, tell me now? Medium parameters. Properties of mediums will depend upon this thing. Right. These are called as medium parameters. Now I am taking the two mediums I have taken now here. Just imagine now. So this is the two mediums, and this left side part is one type of medium and right side part is another type of medium. And in this medium parameters, we can say mu is mu1, epsilon is epsilon1, sigma 1. Here mu is mu2, epsilon is epsilon2, and sigma 2. Right. Now let us consider here. So my electric field is there in this medium which is moving like this, and this is the electric field which we are calling it as E1. Now this electric Poynting theorem, that is for EC, not for electrical, na? Poynting theorem, that is the electromagnetic waves. The topic will come in the electromagnetic waves will come. And this here, this is E1. So you see this thing, this line, what this line will do, it will separate the two mediums. The one which separate the two medium, that is called it as what, tell me now? Boundary. This is called it as what, tell me? Boundary. Boundary is nothing but a junction which separate the two mediums, like a partition. Left side part is one medium, right side part is other medium. The boundary is a plane, not a line. It will appears to be a line, but it is a plane. Now I am taking one line which is perpendicular to boundary. This which we can call it as a normal. This is called it as a normal. Yes. And we are resolving this into two components now here. Now we are resolving this into two components now. And this component, this is one component, and this is a component. This, how this component to the boundary, you tell me now? Parallel or perpendicular? Perpendicular. So that's why this is called as what, tell me now here? E1n. And this is another component. How this component to the boundary here? Parallel. So that's why we are calling it as E1t. Understood? Means tangential components of electric field in the medium 1. E1n means normal components of electric field in the medium 1. And similarly, we can do this electric field in the second medium, that is E2 I am calling. This also we do resolve into two components now here. And this components which we can call it as what, tell me? E2n. And this component is what, tell me now here? E2t. Yes, in the telegram you do message me, BV Reddy sir. There you will get the complete notes आपको मिलेगा. This is the telegram. You will get it. You can search, you can message me, you will get the complete notes there. Okay, so this is what we can do. We can resolve it into two components, E1t, E1n. E2t, E2n. So that means any vector which we can resolve into two components now here, the electric field. So what I can say now, this is E1, which is equal to what, tell me? E1t plus E1n. Next E2, which is also given as what, you tell me? E2t plus E2n. The same thing for remaining also. That is D1 equal to what I can say, tell me now? D1t plus D1n. And D2 equal to what, tell me? D2t plus D2n. And same thing for magnetic fields also. Tell me now here H1, which is given as H1T plus H1N, that is H2, which is equal to H2T plus H2N, and B1, which is equal to B1T plus B1N, and B2 equal to, that is B2T plus B2N. Okay. These are the any vector can be resolved into two components like this, tangential and normal. Okay. Now, so what we do is, they will give the electric field in the one medium. They will ask to find the electric field in the some other medium. Let us say they given this E1 value given. E1 given means they has given E1T given and E1N also given. We'll separate the E1 into E1T and E1N will separate first. Okay, tangential and normal. And I will find the E2T from E1T, E2N from E1N. After finding the E2T and E2N, we can get the E2 we can get now. Okay. From that we can get this E2 will get now. That's what we used to do. The same thing for remaining also. So now that means to get the E2T from E1T, we should know the relation between these two. How the E2T and E1T are related. The relation between the E1T, E2T, E2N, E1N. These relations are called as a boundary conditions. The relation between the tangential and normal components of electric and magnetic fields is called as the boundary conditions. And those boundary conditions we are going to see now here. So totally we have a 4 boundary conditions are there, and 2 for electric field calculations and 2 for magnetic field calculations. Electric field calculation we use electric field boundary conditions. Magnetic field case, magnetic field boundary conditions. So here, first boundary condition you can see. That is what, tell me now here, E1T, which is equal to E2T. E1T equal to E2T. That is what we can say here from this word statement. Tangential components of electric field. Electric field intensity. Electric field intensity are continuous. Are continuous. Same means we can say continuous. That is the first boundary conditions. And the second boundary condition is D2N minus D1N, which is equal to rho s. D2N minus D1N equal to rho s. That is what, tell me, normal components. Normal components of electric flux density. So we got this thing from the Maxwell's equations. We got these derivations here. These derivations from the Maxwell's equations. Normal components of electric flux density. electric flux densities are what, tell me, continuous or discontinuous? Earlier both are same, that's why we call them as a continuous, but these are not equal now. So what I can say now, these are discontinuous. These are discontinuous because of rho s. अगर rho s 0 आई तो again continuous. Okay. Normal components of electric flux densities are discontinuous. Okay. Fine. Next. H2T minus H1T, which is equal to K cross AN cap, where K is called as a surface current density. K is what, tell me now? K is the surface current density. Most of the cases K value 0. Surface current density, and En is what, tell me now? Unit normal vector. En is a unit normal vector from medium 1 to medium 2. Medium 1 to medium 1 to medium 2. Right? Next. The fourth one, that is B2N equal to B1N. That is what I can say, tell me now? Normal components. Normal components of magnetic flux density are what I can say, continuous or discontinuous? Are continuous. Equal na, that's why continuous. Yes. These are the 4 boundary conditions. Yes. Done. Yeah, so this the formula revisions and all we'll do in the one session we'll plan. One special class I will plan. In the special class, I will discuss all the formulas I will discuss. And the special class is on today 3rd na. Okay, 5th we'll do. On 5th we'll do only all the formulas of these things will revise. EMFT formulas in the special class, not the YouTube class. Okay. 5th there is a one class will plan only formula revision. Formula revision only will do. Only formulas only. Okay. On so 5th we'll do this thing. Okay. And so then I will share all the class links. So do join in the Telegram group. I'll share all the class links. I will share it there. Okay. Fine. Yeah. That's it for today. So we'll continue. Next class we'll continue. Next class onwards we'll do ECE topics. We'll do. Okay then. See you. Bye bye.